So this is lesson 2 in the matrices pack. First thing we're going to look at is what we call the identity matrix. So we use the capital letter I to denote the identity matrix. This is a matrix that if you multiply it by anything will give you the original matrix. It's a square matrix with what we call the leading diagonal all being 1s, and then all of the rest of the elements are 0. So typically we'll have a 2 by 2 identity matrix, but you could have a 3 by 3, or you can have as big as you want, really. Just to demonstrate what the identity matrix does, so if we multiply on the left, this matrix A by the identity matrix, we should get just A. So if you do the top row times the first column, so 1 times -1 plus 0 times 1 gives you -1. Top row times the second column gives you 1 times -3 plus 0 times 1, which is -3. And then the bottom row times the first column, 0 times -1 plus 1 plus 1 times 1 gives you 1. 0, 1 times -3, 1 also gives you 1, which gives you the matrix A. Likewise, if we do it the other way around, so we do A on the left, as 1, 0, 0, 1, we will get the same thing. So top row times first column gives you -1 times 1 plus -3 times 0, which is -1. First row times the second column gives you -3. Bottom row times first column gives you 1. And bottom row times second column also gives you 1. So that's what the identity matrix does. It just doesn't change your original matrix. Next thing we're going to look at is what's called the determinant of a matrix. So we're going to look at calculating the determinant of 2 by 2 matrices here. Later on in the pack, we will be required to calculate determinants of 3 by 3 matrices. Only square matrices have determinants. And they are important for finding inverses and when we're looking at linear transformations to do with matrices, which is a later pack. The determinant for a 2 by 2 matrix is calculated in the following way. So you multiply the elements on the leading diagonal, so A times D. You multiply the elements on the other diagonal, B times C, and you take those away. So AD minus BC. If your determinant is 0, we call the matrix singular. And this is because it doesn't have an inverse, okay, because we'll look at this later on. We use the modular sign for determinant, or we just write det m or something like that. Okay. So example 1, calculate the determinant of A. So we do the leading diagonal multiplied together 7 times 3, the other diagonal 4 times 1, and take those away from each other. So that's 21 minus 4, which gives you 17. And just to show you, your calculator can calculate determinants for you if required. It's on a slightly different menu. So I'm going to do the same things I did before. So map vector, I'm putting a 2 by 2. 7, 4, 1, 3. Then if I go for option this time, map vector, here's where determinant is. So I press F3 for det. And I can do det of that matrix there, and it will calculate that as 17 for us. Next, so we've got matrix A, which is in terms of P. It tells us that A is singular. Remember, A being singular means the determinant is 0, and so wants us to calculate the value of P. Well, if we work out the determinant of A, so that's 4 times 3 minus P minus -1 times P plus 2. So that's 12 minus 4p plus p plus 2, because minus next to plus. That gives us 14 minus 3p. We know this is equal to 0. Rearranging this for p gives you p is 14 over 3. Next thing to look at is finding the inverse of a 2 by 2 matrix. So the inverse of a matrix is a matrix that if you multiply it by the original one, you will get the identity matrix. Essentially the opposite, they cancel each other out essentially. For a 2 by 2 matrix, to calculate the inverse, you first need to work out the determinant, and then you do 1 over the determinant on the outside. You swap the elements in the leading diagonal, so AD becomes DA, and then you minus the elements on the other diagonal. So first off, I'm going to calculate the determinant of these matrices here and then work out the inverses. So determinant of A is -1 times 1 Minus 1 times minus 3. So that gives me minus 1 plus 3, which gives me a determinant of 2. This is not a singular matrix, so we can calculate the inverse. We denote inverse with power minus 1, so A inverse is 1 over the determinant, so 1 over 2 on the outside. I swap the elements of the leading diagonal, so 1 minus 1, and I change the sign on the other elements, which gives me this. You can leave it like this. You can expand the half inside if you like. Write a half to go to minus half. And if you do it on your calculator, this is the form it'll give you. You can do inverses on your calculator. So I'm going to again go on to F4 for math vector and put in a 2 by 2. I've got minus 1. Minus 3. 1. 1. And then if I just do to the power minus 1, it'll do the inverse for you. So we get a half, 3 over 2, minus half like we got. Next, we're going to calculate the determinant of B. So we've got 6 times 1 minus 2 times 3. That gives us 0. So B is singular and has no inverse. Of course, if you try to divide by the determinant, you end up dividing by 0, and you can't do it. Next one also has no inverse. C is not square. Only square matrices have an inverse. So that's no inverse. The final part of this lesson is to do with matrix algebra. So this is when you're doing things with matrices without actually writing out any matrices. You're just doing algebra. Here are a bunch of rules that matrices follow that you can use to do calculations, do algebra using matrices. So first one is that matrix addition is commutative. You can do it either way around, but note matrix multiplication is not commutative, which is this here. When you're multiplying by a constant, that scalar that can go anywhere. When you're doing more than one or more than two matrices multiplied together, doesn't matter whether you do the first pair or the second pair. Next one is that you can expand brackets with matrices. We'll probably use this a lot, but if you multiply something by the identity, it just gives you the same thing. Multiplying a matrix by its inverse, regardless of which way around you do it, will always result in the identity matrix. We're going to prove this one here, and you could also look at proving that if you do the inverse of a matrix, you will always get back to the original matrix. So without writing out any matrices, I'm going to prove this statement here, that if you do two matrices multiplied together and do the inverse of that, that's equal to the inverses of the original matrices multiplied together, but notice the order is swapped around. That's important. So I'm going to start on one side of this, doesn't really matter. I'm going to start on the left-hand side and say m equals ab to the minus 1. I want to get rid of this minus 1, so what I'm going to do is multiply by ab on both sides. It matters whether you do it on the right or the left. Well, it doesn't matter whether you do it on the right or left, but what it does matter is that you're consistent with this. So I'm going to multiply on the right. So I've got m times ab, and I've got ab minus 1 times ab. Okay, so multiplied on the right. So I have to put ab on the right of both of those sides. So I've got MAB on the left currently, I've got rid of those brackets. And AB inverse times AB, well, if you times an inverse by itself, it will cancel out and just give you the identity matrix. Now I want to get back to the matrix M. So I'm going to multiply both sides now, first off by B inverse to get rid of this B. I'm multiplying on the right on both sides. And so this B times B inverse here now cancels out, gives me the identity matrix. And so I'm left with MA on the left-hand side and just B inverse on the right-hand side. I don't have to write that I because it just gives you the same thing. I'm going to repeat the process with A inverse. So if I multiply it by A inverse on the right, cancel out with that A on the left-hand side, I'll just get M. And on the right-hand side, I've got B inverse A inverse. Now we've got two expressions for M. We've got one here and one here. So I can set those equal to each other and say, therefore, AB inverse equal to B inverse A inverse as required. And you can quote this result. If you learn this result, you can quote it, and it is useful sometimes. But this is how you would prove it using matrix algebra. This example 3, it tells us that BAB is equal to I. And first off, wants us to prove that A is equal to B inverse. So starting off with BAB equals I, I'm going to times by B inverse on the left. B inverse B gives you I. Cancels out essentially, and you just get left with AB on the left. B inverse I is just B inverse. So that gives you AB equals B inverse. If we do the same thing, multiply by B inverse on the right, again, B inverse cancels out and gives you I, and so we get the result that we were asked to show. A equals B inverse B inverse. It tells us the matrix B and wants us to find the matrix A. So if we use what we've done in part A, then we can figure out what A is. If we calculate B inverse first thing to do then is to work out the determinant of B, 2 times 3 minus 1 times 5, which just gives you 1 for the determinant. And so B inverse is 1 over the determinant, so 1 over 1. Swap the order of the leading diagonal, so 3, 2, and change the signs on the other ones. Gives you minus 5. A then is this multiplied together by itself. So we'll do B inverse times B inverse. Got rid of the 1 over 1 because that's just 1. And then do this multiplication. You could do it in your calculator, but I'm going to do it by hand to practice. So first row times first column gives you 9 plus 5 gives you 14. First row times second column gives you minus 15 minus 10 is minus 25. Second row times first column minus 3 minus 2 gives you minus 5. And second row times second column gives us 5 plus 4 gives us 9.